Good afternoon, everybody. Welcome to this webinar organized by ETIP Geothermal and EGEC. We have a lot of people registered today, more than 500. Hopefully, many of them will join us. So, to allow maximum of them to join, we will start in 2 minutes. Past 2. So, this webinar will be recorded. Thank you all for attending. I know that many people are still connecting, but we have a fantastic agenda. So I wish to have all presenters having time to present their presentation. So I will do just a short introduction to present the agenda and allow people to connect also. So we plan 1 hour and 30 minutes. It may be last 140, 45 minutes. So be flexible with the end of the time because indeed some presentations are so nice to hear, but we will not interrupt them. We'll let them deliver fully their presentation. What is the agenda of the day? The topic is geothermal. More than geothermal is focusing a bit on geothermal exploration with AI and resource mapping, and you can see the agenda. First, we are pleased to see the European Commission from DG Energy, Stavros STAMATOUKOS, to present the upcoming European Commission strategic roadmap for digitalization and artificial intelligence in the energy sector. So really, we are waiting for this publication from DG Energy to see what are the perspectives also on that. As a geothermal sector, we are welcoming such a publication. It was announced in the draft agenda, unfortunately, representatives from the University of Trieste and from the OGS in Trieste are not able to present today their scientific paper. I refer to a scientific paper, so you can have it available online. And my colleague Giulia Cittadini will just give you some view on what is about the scientific paper. We will put the link, and I encourage all of you to look at the first, I think, scientific review of all AI application in geothermal. The agenda today is on 2 specific sessions, one on exploration with artificial intelligence, and my pleasure to give the moderation to Diederik van Wees from TNO, which is also the vice chair of ETIP Geothermal. We have 3 presentations, and I will let Diederik present them in details. We have a short break at about 3 o'clock. And during this break between the 2 sessions, my pleasure to give the floor to Willem Bulthuis to present you an event organized in Munich in October, and today a call to geothermal startups. The second session will be moderated by Huck, the chair of ETIP Geothermal, and will not only look at exploration, but more looking at mapping the geothermal resources. And we have 3 also really interesting presentation on this topic. We'll wrap up and conclude. Before conclude, just give you an announcement. It may happen that next Wednesday, the Commission will announce that they will create a European geological database for geothermal. So be ready, because we'll need all your efforts on AI, on exploration, and resource mapping to make such a fantastic database at a pan-European level for geothermal available. I don't want to say more things except to give the floor to Diederik for the moderation. Sorry, my mistake. No, first, it's me to moderate. Sorry, I was too excited to announce that. It's to give the floor first to Stavros STAMATOUKOS for presenting the European Commission roadmap.
Thanks, Philippe. I hope you can hear me.
Yes, I confirm.
Excellent. So, good afternoon, everyone. I'm excited to be part of this discussion, which I have to confess it's the first time I'm joining your group here, the ETIP Geothermal and EGEC. So I'm very happy. I will give you a bit of backstory of the roadmap and what we are planning to announce next month and the rationale behind it. So, as you know, we already have a digitalization action plan since 2022, and we're proud of it. In the Commission, the energy sector is considered among the most advanced and digitalized industrial sectors. We have a very strong industrial base in Europe, and this is why we believe that the energy sector is a lever to drive competitiveness of digital industry itself. We have big developers of applications. So in the industrial applications, we are among global leaders in Europe. And all these are realities that we acknowledge with our strategies, and we bring forward policy measures to empower European companies to develop and scale globally digital and AI applications. So the strategic roadmap for digitalization and AI, it was, first of all, it was asked by the president of the commission to our commissioner at the beginning of his mandate to present a vision, a roadmap, how the energy sector can digitalize and use AI efficiently and safely. And I highlight here safely because you know that many of the elements of our industry, many parts of our of the energy sector are critical infrastructures that require very strategic and cautious steps. So we have worked closely with the stakeholders of the energy sector, and we have identified three main intervention areas, three pillars that we will address with our strategy. And the first of it is we're starting from the challenges, let's say, of the digitalization and AI, which is the increased energy demand. So the compute or the data center, let's say, industry, to put it more clear, it's about 2% of final electricity consumption in Europe. But the trend is increasing rapidly. So we see new installations of new orders of magnitude that we haven't seen before, of 100 megawatts, 500 megawatts. We even have some announcements in Europe of new facilities of 1 gigawatt, which is something that the energy sector hasn't seen before and possibly cannot accommodate, at least at the pace that the digital industry would have liked. So we have a mismatch there. We have a demand for new power connection from the digital industry that cannot be accommodated by the energy sector and creates certain challenges. And the challenges are mostly local in the places where the demand is coming. But this is, as we see the trends, this will be the case in many EU countries. So, for example, now we see Ireland as a hotspot for data centers, Netherlands, and some areas in Germany, for example, around Frankfurt and in France. But this trend is going to new places, and we need to make sure that the mistakes, not mistakes, but let's say the challenges that these countries are facing will not be replicated. So we started a proactive dialogue with two sectors, with the digital sector, so the data center industry, collocators, developers, operators, and the energy industry. So manufacturers, grid operators, and utilities, to identify the pain points, which obviously is the pace of development. It's the connection request. There is a backlog of long queues, but also operational issues such as fall through phenomenon. So the phenomenon that data centers go offline, huge loads go offline in a matter of seconds when there are certain oscillations in the grid, but also flexibility potential of these data centers. So we are having already a structured dialogue, and the idea is to bring this dialogue into voluntary commitments from both sectors. So what they can bring on the table to improve the transparency of the process of the build out, to improve the speed, so that permits can be given faster, to improve the build out of new grid to accommodate the data centers. All these areas that we are working with both sectors and will be addressed in this strategic roadmap. Another area that we are looking at is the efficiency of the data centers themselves. So as a building, not the integration of in the energy system. And for that, we are adopting next month, together with a strategic roadmap, a delegated regulation which introduces a rating scheme for data centers. So data centers will be assigned a rating depending on the efficiency levels, and this includes energy and water efficiency. And a better rating could potentially link to better or faster siting. This is not obviously still the case, but in the future it could be used to distinguish best-in-class data centers from the less energy efficient ones. So this is one priority area of the strategic roadmap, the energy demand of the digital sector and the AI, and all this is caused by AI, these trends. At the same time, we will be reinforcing our modeling. We will model this energy consumption in different parts of Europe over the next year, so that we can proactively foresee where the build out of data centers will be, so that we can drive this development depending on the grid availability. Objective remains that we can facilitate the digital sector to build new data centers, obviously, but not at the expense of other industrial sectors, and not at the expense of the consumers, individual consumers. So we, at the same time, we try to monitor the market, that new data center build out doesn't bring energy prices up, and does not give any priority access, let's say, to data centers compared to other industrial sectors. So that is the first priority. The second priority of the roadmap is how we can accelerate the uptake of AI. And we don't single AI, but digital technologies, including AI, let's say, into the energy sector. And here I have to say that while the priority is the energy sector as a whole, our first use case, which is the most advanced so far, is the electricity grids. So we are seeing very advanced applications on optimizing the planning and operation of electricity grids. And we are starting as a pilot, let's say, from this sector, but the objective is to promote the uptake of AI applications across all segments of the energy sector. Again, here, a number of initiatives that we're putting forward, like smart grid indicators and a joint bottom-up initiative that the sector itself has started to exchange data. So different operators from different countries to exchange data to train AI models collectively, so that they can share the results and the IP rights of the final product. And that was the second priority. And the third priority is data. So data is the enabler to build applications, to train AI models, to facilitate smart and innovative services, for example, flexibility services. And for that, we are proposing to accelerate a unified European energy data space. We have piloted several data space projects in Europe. Data spaces, for those who are not familiar with the term, is a methodology to exchange data safely between various actors in concrete use cases. I will give you as an example the use case of bidirectional charging of electric vehicles. So here we are looking at transport sector and energy sector. Well, different actors in a value chain, they need to exchange safely data. For example, is the user or the owner of the car, the operator of a charging infrastructure, the grid operator that the charging infrastructure is connected, and any in-between players like the aggregators and market actors that they facilitate this process. So this is a very complex ecosystem that they need access to private and secure, in many instances, data. And the data spaces provide this technology and the governance framework so that data can be exchanged safely between all these actors to facilitate these energy services. So we are expanding this data spaces approach, and it doesn't mean that we collect centralizing any data. This is not the objective, and it's not happening. Data remain with the rightful owners. We just facilitate, we link the different players each other with a secure layer of data exchange so that the data can be exchanged. And training AI models is one of these use cases that we are looking at. And I bring this as a possible input for your discussion later, that data space could provide the technology that data from different sources can be sourced, pulled together to train AI models, which can be trained in a, let's say, federated and decentralized way. So these are the main priorities of the strategic roadmap for digitalization and AI. We had a public consultation after summer last year, and we are ready to publish it. I would like to highlight here that the roadmap will come as an integral part of a broader package. It's called Technology Sovereignty Package. That includes a number of other legal documents, for example, the Cloud and AI Development Act and the CHIPS Act, and it is under a technology sovereignty umbrella, and this gives the message that digitalization of the energy sector is not just using digital tools to make the work more efficiently and faster, but it's a matter of strategic autonomy for Europe. It's a matter of technological sovereignty and also competitiveness. So the objective is threefold here, is to promote the development of European applications trained on European data based on principles that they are set here in Europe, that based on built on transparency, so that users in critical infrastructures know how the applications are developed and how they behave. They have a understanding of the technology behind them. So these are all principles that we are promoting in the framework of this technology package. Open source is also part of an open source strategy, so also part of this package. And it's an approach that we also promote insofar that serves certain business models. We know, we are fully aware that this is not always the best way forward, but it's definitely promoted as we do also through the research innovation programs that we are running. So this is all for now. Also, I would like to close here with a specific reference to the geothermal topic, which is not specifically mentioned in the roadmap. As I said, it's a very short document and very high level, so we do not address concrete sectors. But on the first work stream that I mentioned on the data centers, we also want to see how the data center industry can become an accelerator for certain technologies, for the uptake of certain technologies in Europe. And we have here identified that small modular reactors and advanced geothermal energy could be benefited from the accelerated build out of data centers that could become, let's say, lead the clients and investors in the uptake of such technologies. And this is clearly discussed in the discussion we have with the sector. And we would like to exploit any possibilities there. So this is all from my side. I'll be happy to take any questions if there is enough time. Thanks again for the invitation, Philippe and team.
Thank you, Stavros. Really clear. we understand that it should have been released on the 15th of April, but you have more emergency in the energy, so it's postponed to next month. Anyway, it will be a really good and welcome document. Today we focus on the use of AI for geothermal, but as you mentioned, geothermal is also a provider of energy to data centers, not only for electricity. Of course, we supply 24/7, which what data center needs, but we also know 1% of energy, 30% is for cooling. We provide free cooling to data centers. What is better than just a free cooling to them? And we also allow, they have a lot of waste heat to store in the underground, the waste heat if they want to distribute to district heating. So we are the perfect ally to data centers. But it's not the topic of today. The topic of today is how we use AI in geothermal. Thank you, Stavros. Indeed, there's maybe some question to you. We will look at to that. But now I give the floor to Giulia to present on behalf of University of Trieste and of Observatory of Geophysics of Trieste, their scientific paper. Giulia.
Yeah, thank you. Hello, everyone. I'm Giulia Cittadini, Senior Policy Advisor at EGEC. And indeed, in my presentation, I'm going to present you this paper, Artificial Intelligence in Deep Geothermal Energy, Trends, Insights, and Future Perspective, that was realized by the University of Trieste together with the National Institute of Oceanography and Applied Geophysics. Unfortunately, the author weren't available, but I'm going to present you briefly some key aspects of this paper, which is available online, so you can just download it. It's available there. So the objective of this paper is to evaluate how AI can address geothermal barriers. We know the classic barriers for the sector, by systematically synthesizing its application in deep geothermal research. This paper proceeds in an analysis and a review of around 200 papers analyzing AI methods, application, and performance. So all the data I'm going to provide you is based on this around 200 papers that have been analyzed. So these are the areas, the research areas where for AI application for geothermal energy. So it's around 8 research areas, and this graph shows you which are the dominant research areas. So, and you can see also a timeline at the bottom of this graph. So you see that around 2020, we see a peak in terms of analysis and AI application within the geothermal energy sector. And the dominant research areas are definitely the reservoir characterization, exploration, resource identification, and system optimization. But you can see that in general, we see an increase of attention among all these research areas for AI in geothermal sector. In terms of trends in application for geothermal energy, we can see that before 2019, the interest was minimal. After 2020, we see an increase, rapid growth, which makes around of 75% of annual growth rate, which is quite impressive. Also, it's interesting to see in this graph the comparison with the all AI publication in general. So it's very interesting to see this trend and the increase after 2020. So this for all research areas before we saw for specific research areas. In terms of global research distribution, we see that the leaders are definitely China and the US. Other main contributors come from Germany, Turkey, Canada, and India. So, and these maps highlight in a different way the same result, basically. And finally, in terms of key AI algorithms, we see here the list of all the algorithms that are used in this framework. The most used is definitely the AIN, the dominant. We see also increasing use of other. You see this also applied in terms is it from my side. It was very brief, I know, but you will. I will send you in the chat the link of the paper. I'm sure you're going to read it and enjoy the rest of the webinar. Thank you.
Thank you, Giulia. Indeed, as geothermal, we are really flexible. Just this morning, you had to prepare this presentation because the university was not able. So thank you, Giulia, for your flexibility. You are a real geothermal one. Now give the floor to Jan Diederik. Are you ready to moderate this session? Because also I want to thank you because it was your idea, no, as vice chair of the ETIP to say we should do something because there's increasing application of AI in geothermal. So happy to give you the floor to deep dive on this topic, Jan Diederik.
Thank you, Philippe, and welcome everybody to the first session, which is on exploration with AI. And indeed, as moderator and initiative taker for this webinar, I'm very pleased to see that it's timely and with a strong participation. Without further ado, I would like to invite the first speakers, which are Justin Pogacnik and Arnoud Huck from respectively VITO in Belgium and the Grootbril Earth Sciences. They will give the first presentation, which will be on sustainable and affordable urban geothermal exploration, novel technologies and workflows.
Yes, thank you, Jan Diederik, and thank you, Philippe, for the introduction. So today we're doing a joint presentation. Arnoud and I are involved in the same work package in the URGENT, the EU Commission, the Horizon Europe Commission project URGENT for urban geothermal exploration and novel technologies and workflows, with a focus today on seismic interpretation and reservoir modeling. And so I'll just do, there we go. Just a quick overview of URGENT, and then I'll give the floor to Arnoud. So we're about 2/3 of the way through the project. We began in 2024 and it finishes in 2027. And the goal, right, is decarbonizing Europe's heating sector by developing innovative and low-impact seismic exploration technologies and AI-driven analysis to optimize geothermal resource exploration in urban and sensitive areas. And so as part of URGENT, we have 3 test sites. We're developing seismic source, seismic receivers for seismic surveys in urban and industrial areas. And we also have a large modeling section. And so I'm going to jump straight into Arnoud and the overview on post-processing and interpretation of seismic surveys.
Yes, thank you, Justin. So in our part, what we have focused on is really to improve the efficiency and quality of some of our post-stack seismic filtering workflows. So for that, we worked mostly on a fault-preserving filter, which I'm going to show in directly on the next slide. Then we've done a lot of AI work. We started initially creating a foundational model framework that I'll present as the second part of our work. We've used these AI models to create an interactive update of a 3D machine learning model using interpreted faults provided by the interpreter picked in order to retrain the model. And the last part of our work in the project is to use the AI predicted image to feed in the best possible image into an interactive fault tracker. Justin, if you can go on the next slide. So the edge preserving filter is, here you see just a section of a post-stack seismic data, seeing the raw seismic. So it's a filter we already had implemented a couple of time ago, which was working reasonably well on 3D data, but was not very quick to run. So we've improved its efficiency to make it really easy to use and applicable on very large 3D cubes. And we also made it 2D capable. In lots of geothermal projects, the only seismic data available is a set of 2D lines. That filter was not available at all on 2D seismic data. So this is what we have done. The next slide is showing you the result. So it's a filter which is definitely not amplitude preserving. That's not its objective. The objective is really to make the seismic reflections as clean and continuous as possible when you are away from the faults, but also to preserve the fault expression as much as possible. So you really want to see a very clear offset of the fault on the output image, and clean seismic events pretty much everywhere else. And this is kind of the ideal seismic data that you want to feed into an AI training model. So we want to recognize to basically guide the model and have it use something which is relatively clean. And so as a standard sequence, you would apply the filter on your seismic data and then use an AI model to predict the fault occurrence, the fault probability on it. So on the next slide, we see how we build a new type of model. So we're not trying to, well, we already had convolutional neural network models, UNet models, but this foundation model goes beyond it. So we're still using the same kind of model architecture, but we train the machine learning model in two phases. One phase is a very general training phase. And in order to have this first step of the AI model training to work, you need to feed it an enormous amount of data. So we have collected seismic data available, pretty much public data available around the world, out of 225 seismic surveys. We have selected the data we wanted to use, discarded some of that public data, and eventually gathered about 2 million 2D seismic slices. And from these slices, we want to be able to extract images which are normalized. So they, regardless of the seismic survey, they always have the same image size, 512 by 512 pixels, and unified at a sampling rate of 4 milliseconds laterally, vertically, and 25 meters laterally. So that included a step of data regularization in order to bring all that data into a common bin size, common grid size. So there was a lot of background work to get that done. We can go to the next slide. And the foundation model basically works by selecting subsets of the seismic data. So from the original cube, we apply a mask. So we blank a large part of the existing data, and that mask is then the output for the model. And the first pass of that foundation model has to be able to predict, recreate the original data based on the masked data as a target. So this is a workflow which we run iteratively from all the seismic surveys. We masked the images randomly throughout the available data, trained the existing and single foundation model, and then go to the next data set, re-extracting the data, creating masks again on that second survey, and updating the model accordingly. So this is an extremely iterative machine learning training, which is still continuing, which will eventually give us the optimal machine learning models that we can use to run our fault predictions. So we can go on next slide. So eventually, we from the 215 surveys, we gathered a total amount of 104 gigabytes, and then these surveys range from just about 7 usable images up to more than up to several thousands of images for the large 3D surveys. So that's what we have used. In order to train just a single data from a single survey, it takes a day. So to iterate over all the 215 surveys, it takes almost 6 months. So that's we spent most of last year on that, and a large part of this winter on that, a lot of machine time. After that, we really have a pre-trained fault model, and that unique pre-trained model is then supposed to be applicable on every seismic survey that you would have. And the goal is to use it into the interactive fault-assisted picking of the faults. So what we have is we use the seismic data, we apply the model or any other image fault-specific image technique, and once we have that, we use the extracted fault probability volume in order to use a fault plane extraction mechanism from the final fault planes. Then we can iterate, recreate image masks, retrain the model until eventually we get the best possible set of faults in the seismic data. So that is the kind of, in a nutshell, the summary of that fault-assisted AI tool, AI picking tool. Eventually, in order to the last step of that interactive fault plane data extraction is to convert the ML predicted AI image showing the fault pattern into fault planes. In order to do this, we implemented our fault plane tracker, which can, at the same time, predict single faults out of the AI predicted cube or multiple faults. So workflow would be summarized in these 4 steps. First, you display your data, seismic data, and the AI predicted fault cube on a time slice or a Z slice or an inline or a cross line. Then the interpreter is going to pick seeds, at least one seed for each fault plane to be extracted. That's the step 2. And then the auto tracker is going to connect all the possible voxels throughout the cube in order to come up with consistent fault planes throughout the 3D area. And then these fault planes can be displayed in 3D, validated, invalidated by the user. The user may add more seeds, retrack these faults until eventually you get the fully picked fault planes out of your seismic data with AI assistance. Okay, so this is in a nutshell what we have been doing in the context of that urgent project.
No, great. Thank you, Arnoud. And so then I'll continue on. So what do we do with these structural models in the picked fault planes? And so is moving on to reservoir simulation. And so as part of Urgent, in collaboration, VITO and AGH in Krakow in Poland, we're developing the risk management toolbox, we're calling it. And so faults in a geothermal reservoir kind of represent pleasure and pain, right? If it's especially in a fracture-hosted reservoir, they are your productive regions, your permeability, but they also host induced seismicity. And so the goal of the risk management toolbox is to look at that productivity versus risk trade-off and to try to optimize productivity in some way while minimizing the risk of inducing seismicity and shear failure is what we really look for. So that's kind of the motivation. So what does that look like? The kind of high level what's going on is, so we're developing, it's a Python tool. It's open source, it's hosted on GitHub. You can feel free to download and play if you like. And so the tool is designed for high performance computing for HPC. So it's parallelized, it's multi-threaded, runs in Linux and in Windows. And you kind of enter the toolbox at the well builder, at the configurator. And so that's what it's about, is picking well placements. And so you define an initial, you give it some sort of configuration. Maybe you have a certain shape or a certain trajectory that you're a target zone that you're kind of already thinking, or a kickoff, maybe a wellhead or a kickoff point. And then possible well shapes, J shapes, S shapes, vertical, horizontal, perforation, sections. Also, things like economic considerations are all built in. So like cumulative well length. And so that is all passed from the configurator to the reservoir simulator. We're using Open Darts. It's a TU Delft developed reservoir simulator. And in a thermo-hydro-mechanical simulation. And so evaluating things like heat generation and also seismic risk, right? The geomechanics. So we need to look at the stress changes. All that goes into some sort of risk evaluator. What are you trying to minimize or optimize or maximize? And the user can define that. And then that goes through the optimization engine. And this is the machine learning portion. So we have a multi-objective particle swarm optimization technique protocol that is used to solve the user identified optimization problem, right? I'll go into that a little bit. And so this searches for an optimal well placement. In the example I'll show, we're trying to maximize heat production with a penalty for induced seismicity. So what's the practical problem? So our demonstration case is here in Mol, Belgium. Whoops. It's here in Mol, Belgium, our Balmat geothermal site, the VITO geothermal site. And so we're kind of in the northern part of Belgium, in the red square you can see on the left here. And we're targeting the Dinantian area, lower carboniferous limestone group. The depth of the reservoir in our area is kind of 2,500 to 4,000 meters deep, kind of depending. And it's fracture hosted. So we have an example of a time slice on the right here of our reservoir. And we're using OpenDetect and the DGB for picking faults and things that Arnoud was presenting. And then we have kind of an idealized conceptual model that we're using for developing the toolbox and testing it down on the bottom right. And so this is our basic kind of, say, fault pattern, our fracture pattern. So we have the oldest kind of north-south oriented faults, normal faults in a Horst-Graben kind of setting. Those were perpendicularly cut later on in an east-west-ish direction. And then everything was shear reactivated later in a kind of a third direction. So we have faults in three directions. We have very little karstification in our reservoir. So it's primarily fault fracture-based flow. And we have a lot of induced seismicity. Mol GTO1 is our production well, and GTO2 is our injection well in our doublet. So that's to give you a little bit of context on the setting. And then the toolbox. So what do we do in the toolbox? I've kind of gave you the high level. So how does that practically work out? You have this geologic structural model from Arnoud, and then you have to populate that with material parameters for a static reservoir model. Meanwhile, the entry point into the toolbox we said was the well configurator. So you have well locations. Those are all put together in terms of boundary conditions, initial conditions for a dynamic reservoir model. All right, so we run Open Darts in the toolbox. The toolbox itself is simulator agnostic. You can build a connector and use a different simulator if you wish. That solves for a pressure and temperature field. And then we evaluate the stress change on the faults in our case, right? That's where we're hosting seismicity. That's what we're interested in. We have a couple different evaluation techniques built into the toolbox, kind of a semi-analytical, direct pore pressure, direct thermal stress calculation, and also a fully geomechanical finite element geomechanical solve as well. If you're doing some sort of single objective optimization, you just want to maximize heat production with a penalty on the heat or on the flow. If you've reactivated a fault, you can continue to iterate there. Or we can do a multi-objective optimization where you're, say, trying to maximize your heat while limiting the amount of induced seismicity. And what we're looking for there is number of reactivations, trying to minimize the number of reactivations. And so that can go to the optimizer and you can loop there. So that's kind of the basic flow of the risk management toolbox. And so then the particle swarm optimization framework that's part of this. AGH and Damian are kind of, at AGH is kind of the primary author of this. So if you have questions, I encourage you to talk to him. You can get in touch with me and we can put you in touch as well. But so in the particle swarm optimization technique, one cycle of that kind of looks like, okay, you have to populate a list of control vectors. These are, the well locations, right? So you operate this in some sort of batch mode. You're running 10 or 20 realizations of different well locations in a generation. You run the simulator for all these. You can do that in parallel. And you have your objective values, your heat flow, your seismic reactivation, whatever you're looking at. And then you can look at, is this within the bounds of acceptable? Is this good, bad? In the multi-objective case, we have to consider things like non-dominant trade-offs. Do you have high heat flow with lots of reactivation, or do you have very little reactivation but low heat flow? And so all these things have to be considered by the optimizer. And then that goes to define the next generation, the next population, right? And then it populates the new well locations. For a little bit of ML speak, let's say, for making sure that we're finding, for robustness, that we're finding a global optimal point. We're trying to preserve diversity as well with grid pruning, crowding distance, mutation. And so then you move on to the next generation, right? So that's the basic flow there. And here's one example from our test case. This model I presented earlier with this kind of simple fault structure with an original well location is given by these purple X's in the top right, with the injection well at the far right and the production well here kind of in the middle. We're looking at we're restricting our search bounds in this area around the faults to make sure we're fairly close to the faults and not just finding something off in the corner. And so then we allow the toolbox to go through 20 generations. Each generation had 10 realizations within it. And so you can see kind of the guesses that it went through as time went on, all in this area, within your bounds. And you see, so you're kind of spamming the whole space, but also it's starting to crowd around optimal areas to make sure it's finding true global minimum. For the initial well locations that we put in, the heat delivery was 7.35 megawatt years. And those were penalized pretty heavily because they were close to faults. So the flow rate was continually penalized, quite a low flow rate in the end. And then the plot on the bottom right, what we have is the average values from each generation, the minimum values, and then the maximum. So you can see that the heat kind of reached a maximum. It found the maximum within about the 10th generation. And then in that case, that was 22.5 megawatt years. So quite a large improvement. We're working on the multi-objective optimization now. And the goal is then to, instead of just blindly penalizing heat flow rate, let's try to optimize that as well as we're moving. So that's where things are going. So that's our test problem so far. What are we doing now? We're extensively testing it, testing the different types of well shapes, the horizontal wells, kickoffs, things like sidetracks, making sure all this is working properly. And eventually we're going to move to a higher fidelity Balmont model based on our 3D seismic survey and the actual fault traces, not this idealized setting, and with the multi-objective optimization going. And at the moment, also working on adding the well control capability. So it's going on. And the next step also is adding optimization restore points. So to make sure that that global minima is robust and it's not just a local minima is kind of the basic idea there. So I thank you guys very much. Here's a list of names for contacts. And that's a little bit of what's going on in Urgent with AI. Yep.
Thank you very much, Justin and Arnaud. Very nice talk. We are running a bit behind schedule, so my suggestion is that we move quickly on to the next presentation, which will be by Elisenda Rodriguez from Seequent, which will be on AI for geothermal exploration. So please, Elisenda, take the floor.
Thank you. Can you see my screen?
Yes.
Perfect. Well, thank you so much for joining us on this presentation, AI Power Core Imagery for Geothermal Exploration. My name is Elisenda Rodriguez. I'm a senior geologist working at Seequent, and today I want to show you how core images can become real geothermal data and geological inputs, not just pretty pictures. 1 second. The slides are not moving. Now, so in geothermal, drilling is expensive, it's slow, and it's irreversible. But every every well also produces core images that capture fractures, alteration, recovery, that are critical information that is often underused. Today, I will demonstrate how standardized image capture and AI can turn those images into geological data that we can actually trust. So, what if we start treating core images like first-class geological data? Imago is a software built specifically for geoscience image capture, management, and analysis. The idea is very simple. We are going to standardize images at the source. We organize them automatically and make them immediately useful and available for geological interpretation and modeling. Once images are captured, Imago uses machine learning to automatically crop and linearize core trace. The images are organized by depth, by drill hole, and stored securely in the cloud, ready to be reviewed, compared, and interpreted. This is where images stop being files and start behaving like real geological data. On top of standardized images, Imago now includes an AI-powered image analysis. Directly inside the Imago app, we can extract structured data like RQDs, fracture, and color, consistently and at scale. And this isn't a black box workflow, it's a human in the loop, so geologists can validate, adjust, and edit all the outputs. And because this is AI-derived data that is generated from trusted images, it can directly flow straight into the geological workflow and on our models. So now, let me show you how this looks like in real practice with a real drill hole. Here we are seeing the Imago portal on a web that is displaying one single well that have a continuous amount of rock, and it's coming this image from the original one that has been already cropped by AI. In the portal, we are going to be able to use this information and analyze the images as well. So we can click here to open the image analysis tab that is going to allow us to run the image analysis and to review the data that has been already collected. We can display the autocrop that is going to be the boundaries of the boxes and as well the trace to use the linearization. We can show and display core conditions and including the show segmentations. If I zoom here, we're going to be able to see two different types of rocks. In this case, one is completely fragmented and it shows like that, and the other one is a continuous piece that it is going to be even recording the gaps, just here. If any of this data that is generated by AI have any errors, we are going to be able to analyze them and change them. So we can edit those by just clicking on the specific segment that we can change, and we are going to be able to recategorize. And once these edits has been done, automatically saved on the cloud, we are going to be able to run the images analysis again to apply for the calculations. We can also display here the fractures. As we can see, these are the fractures that has been identified by the AI, and we are going to be able to categorize from mechanical breaks and natural breaks, and also AI is calculating the depth marks. So here we are going to be able to edit the depth marks using the depth blocks as well. All of this information is going to be stored on the images and as well in the way of, on tables. So here we have the dominant color that has been extracted on these specific intervals, the RQGs, the fracture counts, and the percentage of solid. These tables that are going to be generated as well with the image analysis can be run at the same time that the segmentations and the core condition. It takes around 600 meters, will be 2 minutes of processing, and we are going to be able to select the specific interval and see the display here in the, let's see here. in the image. So we are going to be able to compare those with the data that has been taken on the field by our geologists. All of this, we are now able to export it into Leapfrog. So we are going to be able to see the colors, the RQDs, and the photos on the 3D. So if we go to Leapfrog for the modeling, I'm going to be able to open a model and have the different wells. We can see the images directly on the 3D or in our panels. So here I'm comparing two different drill holes. We have the pink one here on the left side and the blue one that is displaying, but instead of displaying just the core boxes, I'm going to display the trays. So it's going to crop each of them, and I'm going to be able to move from the intervals and know which part of the drill hole I am. So you are going to be able to review the modeling as you go, instead of just seeing and looking what somebody has described on the field. We can actually directly see it on the 3D. And we are also going to be able to include our tables. In this case, we have two of the extracted colors from Imago analysis. We have the RQDs that are by the side of my image, and as well, I'm going to be able to import the colors that has been extracted. So we are going to be able to use it as well to look for alterations or specific features that are embedded on our lithologies. All of this can be exported as a CSV file, every table, and you are going to have the link that is live with your data, which means as soon as on the field there is people capturing images, you're going to be able to see it on the portal and then streaming those directly into Leapfrog. This is mainly what I wanted to show you, so I'm conscious about time. If anybody have questions, we will be happy to have a deeper talk together. So this is everything from our side. Thank you for watching. Back to you.
Thank you very much, Elisenda. Beautiful talk. Then I propose to move on to the next presenter, which will be Rehg from Ignis Energy, and to take the floor for a presentation on using AI and machine learning to screen new potential sites. Do you manage to get the slides, Danny?
I have it ready. Good afternoon, everyone. Moment guesser. Danny Rehg is here with us. I'm a reservoir engineer with Ignis Energy. I'm gonna be presenting today. Let me share my screen here. Let me know when you can see my screen.
Yes, we can see it.
Yes.
Okay, perfect. Okay, so I prepared a few slides to walk you through a high-level summary of some of the work that we've done here at Ignis Energy, and in order to optimize some of our geothermal exploration efforts. So just to state the objective clear, I like visuals and I like questions. So I'm gonna start by just stating our problem that we were trying to solve, and just with the satellite image that you have in mind, the problem that we had initially, if we're trying to find where are the geothermal fields in on this map, there are only two possible ways you can go about this. The first one is you can go and turn every rock and evaluate every data point that we have, and take a decision based on that. But now think about the amount of resources that you would have to deploy and time that it will take to evaluate all of this acreage. The satellite image in front of us is around like 5 million acres. So I would say it will take quite some time. And also, what adds another layer of complexity is some of these regions don't even have data available. They're completely greenfield. So we don't have data to evaluate in the first place. The other option is we can build a tool that can guide us in the right neighborhood, and then deploy these conventional resources that limits the acres that we're looking at, and even gives us an edge to maybe look where no one else is looking. And this is what I'm going to be presenting today. So with this vision in mind, we started thinking about building a data-driven tool, an AI tool that can take us, that again can guide us in the right direction to optimize our exploration efforts. And with that, we started thinking about where we're going to start this tool. And with this, to answer this question, the Western US was with a perfect candidate, not just because it's one of the places that has the highest elevated temperature gradients, but also from the data availability point of view, because Nevada, for example, has the greatest number of geothermal fields and geothermal power plants among all provinces, literally on the planet, which of course resulted in a lot of data that we can use, which is a great starting point for our machine learning model. At the same time, since we wanted to build a regional tool that's not limited to one field or one region, we started thinking about like what kind of data we can use. And we wanted to find a source, a data source that's not that provides at least good or decent coverage to most of the areas that we are interested in. And for this task, Project Innerspace was a great candidate. And with if you don't know Project Innerspace in a nutshell, it's a DOE funded program. It aims to makes geothermal exploration easier. Basically, they have a lot of layers there. I'm going to explain what layers mean in a second. And they started mapping layer in Africa, and then they moved to include the rest of the world. The US now is the most mapped country, and they have more than 400 surface and subsurface layers. And again, just to give you an idea really quickly about what I mean by that, by layers. So basically, these are just some screenshots of Project Innerspace interface. They basically provide some key features that we would be interested in geothermal exploration in the form of color legend. So the color would represent something. And this was the starting point. And since we're talking about colors and images, we started thinking about computer vision in assistance of or in integration with machine learning. So for this task, we went ahead and we captured high resolution RGB images. And then, I mean, I'm not going to spend too much time on the technical side. I know we're running out of time, but if you have any questions, let me know. But of course, like we've done all the pre-processing, and we spent quite some time on selecting the features that we're gonna use. I mean that of course in that we relied on so many things: domain knowledge, literature review, and even some machine learning feature selection. And then we collected all of these layers that we were interested in, and then we fed them into machine learning, the algorithms that we decided on. And for this task, we used 10 different algorithms. They range from deep learning models, reduced order models, and just some decision trees and others. And then after training, deploying, testing, validating the results, instead of just choosing one model and moving forward with it, I mean, I'm assuming like everyone who worked in AI before knows every algorithm has their own biases and inherited weaknesses and strengths too. So we decided on using a hybrid approach. So and instead of just using one or two models that we like the most, the ones that gave us satisfying results, we used the stacked decision based on all of these models. And I will show you how we get the results here in a second. So this is just a satellite image where the white circles highlight where the known geothermal locations are. And the output of the machine learning that we're getting is produced in a form of a heat map that looks something like that. With the hot colors means a high potential of having a geothermal field, and the cold colors are the opposite of that. And as you can see, the white circles are basically highlighting those bright spots. that we see on this map. But if we take a closer look, these are not the only highlighted or the bright spots on the heat map. So the green squares are highlighting some of these also like high potential geothermal fields that we're seeing on this probabilistic map. So this would be a great starting point to start looking. If you're trying to find a new field, you would start with where the map is telling you there could be a high potential for geothermal space. Another great feature for having multiple algorithms is the fact that you can actually vary the confidence you have in the model from just a very optimistic combination of how you stack these models to a more conservative way where you have more confidence that probably these locations will have high chances of having a geothermal location. So you have this flexibility. So going back to the first question that we started with, you can just now deploy the heat map that was created for this region, and this is actually it has some known geothermal fields, and you can see that it actually aligns very well with the trend of the geothermal indication that we're getting from the geothermal map. Really quickly, at this point we've used this model to survey more than like 100 million acres, actually more than that, like maybe a couple of folds more than that. And we've evaluated more than like 150 opportunities, or maybe over 200 opportunities at this point. But I just want to share two opportunities with you that we think are pretty nice. The first one, I don't know if you're familiar with how the geothermal leases on federal land is awarded in the U.S., but the way it is basically a bidding. It goes through a bidding session, and the company that bids the most gets the lease. Gets the lease. So part of our evaluation efforts for these leases, prior to the lease sale, we went ahead and we applied this machine learning tool. And I would say it's more of a workflow. It's not just the tool. We, of course, combine it with other things as well. And then eventually we come up with ranking for all of the offered parcels. And the chart that you see on the right here has two lines. The blue line shows our ranking for each of these parcels. And the other line shows how much these leases were sold for, basically. And you can see this nice correlation between what we rank them as, what we think the value is, and how much they were sold for. Of course, it's never going to be a perfect match. It's a bidding lease, so people have budget and other things as well. So it's never going to be a perfect match, but I would say this is as perfect as it gets. It was like 70 something percent correlation between the two lines. The second one is a project that we acquired recently, and we've also run the machine learning on this part, integrated it in our AI workflow, and we have acquired this lease. Actually, before acquiring it, we went and did some geophysics on the lease, and then the geophysics came positive. You can never be 100% positive with the geophysics. It's still, until you drill wells, there is no 100% certainty. But came back positive. Then we acquired the lease, and then we went back and we did some further de-risking, and the results have been confirming the potential that we have been seeing on the AI map. So with this, I would just like to conclude really quickly. So we have built this code that we are very comfortable with. We've been using it for almost 2 years now, and so far the results have been really satisfying for us. It's very resource efficient. It compared to conventional ways, it takes much less time, and of course less resources allocated for this task. It's transferable, can be applied anywhere else. We actually applied it to other regions of the world too, not just the US. We've applied it to Southwest Asia, and yeah, completely different basins, completely different structures. And we also have been getting really good results. And This is it for me. If you have any questions, please let me know.
Thank you very much, Mohamed. There's one question in the question and answers, but I would propose, given the time, that it will be handled offline.
Okay, perfect.
But thanks again, and then I would like to give back the stage to Philippe, or maybe straight.
Yes, thank you, Diederik. Indeed, what I see that there are so many interesting presentations that probably it will deserve not in a webinar, but probably during the next Geothermal Innovation Days in presence event, we will have a session on that because we need much more discussion on how to use this fantastic tool now by Seequent, Ignis, and by the project. Thank you. Let's use now 2 minutes to give the floor to Willem because we need also to help startup doing also activities in that area to be better financed. And let's give a floor to Willem to announce the call.
Thank you very much, Philip. Let me share my slides just very quickly. I know we are running out of time, so I'll try to keep it as short as possible. And this is a short preview because we are not yet officially public yet with this event, but thanks to Philip, this is a sneak preview for this audience, the friends of EGEC, so to say. We are organizing, we means the TIM-INT organization, which is a joint organization of the Technical University of Munich and the Bavarian state around Munich, where, as you know, there are a lot of geothermal activities. And myself, Corporate Ventures Advisory, in collaboration with TechTour, which is the largest network of VCs and corporate VCs in Europe. And also thanks to Philip, in cooperation with EGEC, we are organizing an event on October 6th to the 8th in Munich, which we call the European Geothermal Innovation and Capital Summit. And this is indeed a European event, a truly European event. It's also about the sovereignty of Europe. We need more geothermal energy solutions in Europe, but we also need to do that more innovation and especially also investors, both venture capital and project investors. This is the scope of the event. So we really plan to bring together all the stakeholders to have a dialogue on how to speed up the adoption and the scaling of geothermal applications in Europe. So we will have there invited ventures, so startup scale-ups, that have innovative solutions. We also will allow and make it possible for geothermal projects to pitch there if they are looking for either investors or technical partners, technology partners. We will definitely have quite a lot of investors there, both venture capital and project financing, project developers, energy companies and off-takers like data centers, as mentioned before in the introduction by the EU. Also insurance, legal and regulatory experts. So we also will talk about what is the challenge there and what are the possibilities, research and development, and of course, very important, big key technology and service providers in this space. So all the stakeholders that are relevant to make things happen. That's what we want to do at this event. We also, if I move, can talk a little bit about the scope. So the scope is primarily deep geothermal energy, geothermal storage, next-gen geothermal technologies, both electricity and heat applications, but also adjacent topics like minerals mining, white hydrogen and CO2 storage will be addressed. And as mentioned, we cover the whole range of themes from innovation to ventures to projects to financing, regulations, business models and risk management. So everything that we need to address to make things happen. The program looks like this, and just to focus on the key things, on the October the 6th, there will be some pre-events, including some site visits to geothermal sites around Munich, including Ever, of course, as you might expect. We are organizing that. On the first day, the October the 7th, we will have some workshops on securing capital, how to organize project financing, what about regulatory developments in Europe. But we also will have there a couple of presentations, case studies by next-gen geothermal projects to learn from them. And that's marked here in blue. We are currently starting to look for projects that want to pitch there, looking for investors, for technology partners, or for other support. And on the second day, besides keynotes and discussions about how to overcome the barriers to scale up geothermal energy in Europe, we will have a platform for ventures, so startups and scale-ups to pitch there in front of both customers, partners, and also investors. That's what we are here for, as Thomas mentioned already. So for the two blue parts, we are about to start the open process for nominations. As mentioned, we are not officially public yet, but this is a sneak preview. For the ventures, we are looking for ventures in those areas: innovative geothermal technologies, alternative applications, synergetic applications, planning and operations, drilling and operational equipment, and also safety and sustainability solutions. So in those six topics, we can start to look for interesting ventures. Now, what's the process for that? We have a nomination process because the event will be invitation only. There are no participation fees, but it's invitation only, and we want to have a good mix of people from all the different sectors. So what we are currently starting with is a nomination process. So if you, or in your context, in your environment, you have good ideas, you want to nominate either a project for case studies or project that want to pitch because they're looking for investors or technology partners. If you are yourself a venture or you know ventures that would fit very well in this program, you can nominate them. Or if you want to participate yourself or have a suggestion for who should participate in this event, you can also nominate those people. We have, unfortunately, a maximum capacity of 100 people at the event, so it is invitation only, but we are planning already a bigger event in next spring, so this will be the starting point for a range of events, hopefully, to talk about how to speed up the deployment at scale of geothermal in Europe. If you want to make nominations, please send me, my email address is here, a very short email with the subject matter EGEC 26 in the subject matter, and then we will start a process. We will launch in a couple of weeks, we will launch a website to register, to apply for those people, just to make sure that we are all clear about it. So both the ventures and the projects that want to pitch there will have to go through a nomination process. So they will be asked to provide some information about the project, about the venture, including a pitch deck, etc. And then we will select in a selection committee the ones that will be invited to be at the event. That's it in a nutshell. Philippe, I hope that gives a little bit of an advanced organizer of the event coming up. And again, Philippe, also thanking you very much for your support to make such an event happen. And thanks for the opportunity to promote it here. Thanks.
Yeah, indeed. And we will send further information later to the relevant people. Hope you digested the first session, which was full of information, because now we have another really interesting session on the resource. And I give a floor to Luca to moderate this session number 2. Luca, floor is yours.
Yeah, thank you, Philippe. Thank you, Jan Diederik, and also all the speakers of the first session. Yes, it was indeed very dense and very interesting. I think that we are seeing from different perspectives the same approach, which is to simplify geothermal de-risking and increase geothermal knowledge at a lower, let's say, expense of resources. So that's absolutely where we are all looking at. And I think now we can move to the second part, and this is going to be a very connected matter to what we have seen in the first part. And we move from the exploration methods to something that is equally critical. So how we map and we understand the geothermal resource itself. Because in the end, better data and better mapping are really what turn potential into bankable projects. So in this session, we look at some European initiatives, data infrastructures, and AI-driven approaches, which are improving our ability to characterize the subsurface and reduce the uncertainty on the resource. So let's start immediately with Tim Debacke from Geognostics, who will present the Seebase initiative and its relevance for the geothermal development in Central Europe. So please, Tim, you can proceed.
Okay, thank you, Luca. I'm going to share my screen and then probably put it in presenting mode. Yes. Can you see it all right?
Not yet.
I am presenting.
Maybe you have a 2 screen and
Yeah.
you're not showing the right screen probably.
Share. Yes.
Yeah,
Can you
great.
see it now? Okay, thank you.
Perfect.
Sorry for the delay. So yes, I'm Tim Debacke. I'm part of Geognostics, and what we are here to present is the Central European Seabase model, and derived from there a geothermal model, which was developed together with OMV and which is free to use and to download. Now, let me see how. Yes, okay. It's a bit slow on moving. All right. So what you see here is a depth to basement map of the world. So this is the base of all the sedimentary systems of the world, and it's hand contoured. Now, what we do at Geognostics is we actually study basin systems starting from characterizing basement, economic basement. This may sound a bit strange, but actually it's quite logical. It's actually the response of the crust on tectonic deformation or tectonic forces that actually determines whether or not a basin will form in a certain place and will be preserved. And it's also that basement that actually determines how heat moves from the mantle to the surface. So characterizing that basement is pretty important. Now, we're talking about Seabase. Our product is something that we call Seabase. What is Seabase? It is actually a comprehensive multi-layer interpreted model of basement. And it doesn't only contain or comprise depth to basement, but also basement composition, depth to moho, etc., etc. We do it via an iterative bottom-up approach. So we start from characterizing basement and moho, and we gradually integrate all kinds of components in there. We think about the tectonic history, we incorporate the basement terrains, the basement terrain history, the basement composition, and that's how we actually build a model geologically. We don't really use AI for this. This is really geological reasoning, geological thinking. And the original approach in this is that we managed to move away from, let's say, real geological data by using gravity and magnetic data. So in any given area, we take the geological data, cross-sections, wells, and we use those real geological data to understand the gravity and the magnetic data in that particular area. And that way, we can actually then move away from the real geological data using the gravity and the magnetics and actually do an interpretation in a part of the area where we don't have data. To simplify this or to explain this a bit better, here you have a map where you have a whole bunch of, let's say, section data, seismic cross sections, a whole bunch of wells, with data points on depth to basement. And so if you would grid these depth to basement points, you get a map that is not really that meaningful. But actually, if you have good gravity or magnetic data present, here it's gravity data, and you start to interpret the gravity data using your real geological data, and you incorporate the tectonic history of an area, the basement terrains, the basement composition, etc., then you have a very powerful insight into the area and into the meaning of the potential field data, in this case, gravity. And then your interpretation of depth to basement looks completely different. Here you have a depth to basement model that is actually telling you something, that is telling you structure, and that looks much more realistic than the example on the left. And so we have been doing this around the globe in different resolutions. And in 2023, OMV from Vienna came to us and asked us to do a high-level update of Central Europe, which we did. It was finished in 2024, and OMV allowed us to release it, and hence we're releasing it to the community. So everyone around the world can download it via the QR code and can use it. What you see on the left-hand side is what we already had before this focus study in 2024. On the right-hand side is actually the improved depth to basement model for Central Europe. But the product includes much more. There's depth to moho included, basement terrains with a whole bunch of information on the geology, the basement terrains, major lithospheric structures that are there, basement composition, obviously the depth to basement map, and then also an interpretation confidence map, which is actually a series of overlays that gives you a feeling of how confident we are about a given interpretation on depth to basement in a particular area based on data quality, difficulty of geology, etc., etc. Now, it's not the first time that we release, let's say, a Seebase or depth to basement model like this. We have been doing it in the past, or our predecessor has been doing it in the past in Australia. And there it became a real success. We released it more than, well, something like 10 years ago, it became open access. And since then, governments have been asking us to update with new data, particular areas, which has then always been incorporated into the overall package. And this serves as a really important pre-competitive geoscience data package that is continuously used in Australia. And we're hoping that also in Europe, this will be used as such, as a real important foundation data set. Now, second part of the talk, now that we have it, now that we've explained how we work, and now that we've explained why we think basement is so important, we always have been doing heat flow, and we always have been doing heat flow. And now with the advent of more and more geothermal models, we realize that perhaps we can offer an original and better solution to many of the models that are around. And two things that we always found strange is that usually in geothermal modeling, what people do is they take very shallow temperature measurements and then extrapolate it to depth, even though people don't really know what the conditions are at these depths, but they get extrapolated towards really deep levels. And whereas heat moves from bottom to top, as you know. And another thing is, well, there's a lot of geothermal, or let's say heat flow models around, but they're not really geological models. They're more data interpolation models between data points, heat flow data points. So we thought we can do better. So why not build a bottom-up conductive model that takes into account true lithospheric geology and actually builds a model, a heat model that goes towards the top and that is calibrated with heat flow data. Yeah, so a geological bottom-up conductive basement heat flow model starting from the lithosphere-asthenosphere boundary, and that at the surface obviously is calibrated with heat flow data. In order to do that, we subdivided the lithosphere into 4 main packages. So the upper mantle, the lower crust, the upper crust, and the sedimentary package. All these units get thermal conductivity values, get heat production values, depending on the lithologies that we can identify. Some packages are subdivided, others are not, depending on the local conditions. These values are attributed, and gradually we build a model upwards from the lithosphere boundary towards the surface. Now, important here is what happens in the upper crust. That is something that often people forget. In the upper crust, there is a radiogenic heat flow contribution that depends on the composition of basement in that area, and that is really important for heat input at the base of a sedimentary system. Now, in order to build that model, what do you need? Well, you need a whole bunch of data. You need a lithosphere-asthenosphere boundary. We have this, or we can map it. Depth to moho, we map it. Basement thickness, we have this. Radiogenic upper crustal thickness, we have this. Radiogenic heat production in the upper crust, that is something, we have the upper crust, we have the basement composition. We take values from the literature, attribute these to the basement compositions, and then we can calculate the radiogenic heat production. Sediment thickness we have, heat production, thermal conductivity values are obviously from literature. And where relevant, we also add transient heat flow. Transient heat flow is actually the heat from a past, not so long ago, tectonic event that still lingers and that gradually diminishes with time. But it adds to the present day heat flow, so you have to add it. Here, the left-hand side, the big image is actually the result. This is the heat flow model, total heat flow at the surface that our model predicts. Now, building a model like this is not something that you do one morning when you get up and say, right, we're going to build this. It actually takes time. You have to think hard about how you're going to model oceanic crust, how are you going to model continental crust, what are you going to do with hotspots, what are you going to do with rift basins, what are you going to do with pull-apart basins, etc., etc. So it's a really, really step-by-step process. You continuously build it, you check it. And we've always checked it with the International Heat Flow Commission data points, different itineraries, different processes, going back and forth, refining the model, also accepting very big or taking very strict rules. You can't just change mismatches so that it matches in a certain area. No, you have to make sure, like, okay, that's this type of basin, so it doesn't work, this type of basin. Then I have to use this approach for every such basin around the world in order to make it fit. So it's a really step-by-step processes with a lot of repeats and redos. But eventually we're there. Eventually we're there with a project, with a result that really works. And so this product includes also mantle heat flow, the different components of the model, upper crustal heat flow, transient heat flow, here only for the rift basins, pull-apart basins, and back-arc basins. Heat flow at top basement, temperature at top basement, geothermal gradient, etc. Now to conclude, it's good to compare this with existing heat flow models for this part of Europe that are often used, but to show you the differences. So for instance, here, Goutot Batal, it's data interpolation mostly. And what you can see is you can recognize the cool East European craton, and then the really hot Pannonian Basin, and a hot region here, which let's say the Upper Rhine-Graben. Davies shows the same, but then different. Yeah, so it's kind of shifted based on the interpolation method. Then you have Lucasso. Lucasso is often cited, often used, but here you see that it's data point heavy. You see the individual data point, so the interpolation is completely different. And then this is our model. This is our model. What we can see here is that you recognize geology immediately. You can recognize geology. The main advantage of that is that we know how it's built. If there's mismatches, we can also explain it in a geological way. We can go back to the drawing board, we can rethink it, we can think what is happening. Some of the mismatches are really easy. For instance, let's say convection is something that we immediately recognize because this is a conductive model. So along major fault zones, convection, that's something that we can't model. But also things that happen in your basin, for instance, the presence of salts will immediately be reflected because of the very high thermal conductivity of the salt, etc., etc. So, but to conclude, the product is available. You can download it via the QR code. Please use it. It has two main things. One is a crustal model, the Seebase itself. The other one is the heat flow model. Please use it. It's all based on basement work, but please use it. Come back to us. Let us check things. Let us work through it. Ask us to do redos in particular areas or updates where you have extra data, because it needs to be tested and it's freely available. Thank you for your attention, and happy to answer any questions.
Thank you, team. Thanks for your very good presentation. And now we can move from this regional initiative, which covers, by the way, a big part of Europe, to an even broader European perspective on data infrastructure. So we have Annamaria Nador from Hungary that will introduce the European Geological Data Infrastructure that will play surely a key role in harmonizing and making the geological data accessible all over Europe. Annamaria?
Hello, yes, thank you very much. Good afternoon, everybody. So I would like to share my screen with you and quickly go through this presentation. So you see my slides?
Yes.
Yeah, okay. So what I would like to briefly present you is basically the ongoing work and the first products of a very large project called Geological Service for Europe, which is actually run by Eurogeo Surveys, which is the umbrella organization of National Geological Surveys. And the overall, this project, it covers entire Europe, so 37 national geological surveys, and we are working on different areas, not only on the geoenergy resources, but also on raw materials, groundwater, coastal areas. But of course, in this presentation, I would like to focus on the geoenergy, especially the geothermal energy. But basically, in all topics we are covering in this project, the main aim is to develop and make permanently available pan-European geological data and related information via the so-called European Geological Data Infrastructure portal, which is a publicly available online portal. And the aim is to pool all the national information from the National Geological Surveys into this portal. But as I said, I will focus on one specific product of this project, which is called the Pan-European Atlas for Sustainable Geoenergy Capacities, which includes not only geothermal energy, but subsurface storage capacities, including hydrogen and CO2 with harmonized maps data sets. So the atlas, and now I'm focusing on the deep geothermal part of the atlas, the concept is basically a data-driven bottom approach. So at the beginning of the project, we collected all previous historic information from the famous European Geothermal Resource Atlas map published by the Commission, from previous projects like GeoELEC, GeoDH, or ESTMAP. But the important contribution was also the national databases from the National Geological Surveys. And what we did is we updated and expanded these data sets and generated new data layers. And this leads to the compilation and creation of this new pan-European EU Atlas. The concept of the atlas actually is based on the play-based exploration pyramid originally coming from the oil and gas industry, which was then adopted to geothermal by Inga Möck and her colleagues, which is basically at the first level focusing on very large scale systems like geosystems, which have similar tectonostratigraphic settings. Then it goes further on a narrower scale to the play focus, so the identification of different geothermal plays. And then within the plays, then they are identifying different prospects, so prosperous reservoirs. So basically we followed this logic or adopted this logic and working method to our atlas. And we defined 3 main levels, but also started with level 0, which is the presentation of the data themselves, because as I said and would like to emphasize, this is a very important aspect of this project, that we really want to provide open access to the basic data themselves. And then we go further to the next level of mapping favorable areas, plays, reservoirs. How this looks like in practice. So if you go to this European Geological Data Infrastructure portal, you can see the URL access here, and go to the map viewer part of the portal. Then on the list of the layers, you can have the different boreholes and for geothermal energy, the thermal springs and other information. And if you look at this zero level information, so boreholes and wells, altogether we collected more than 55,000 objects, which is, I think, a very impressive number. So more than 55,000 boreholes or thermal water wells, among which you can screen according to the depths, the bottom hole temperature, the drill of the year, the country in which was drilled. And more importantly, if you click any of these wells, then in a pop-up window, you get the detailed data on the selected object. So you get all the borehole information, the name of the borehole, the coordinates, the purpose, the drill depths, and other really important informations from the borehole. And also importantly, with a link to the original database. So if this borehole data, for example, was provided by the Czech Geological Survey, then it links to the original database of the Czech Geological Survey. This is just an example. Similarly, we collected thermal springs from all over Europe, and we have about 2,400 thermal spring data collected on the portal. And here, similarly to the boreholes, you can make screening according, or you can make selecting or searching according to temperature, to the flow rate, to the hydrophases, or even to the country. And similarly to the borehole, the features are the similar. So if you just select an interesting spring for you and you click on the dot, then you get the pop-up table, you get the detailed data on that selected spring, again with a link to the original database where it can be found. So this was level 0, the basic data. And for level 1, what we called favorable areas for deep geothermal prospecting, we followed the classification and the system of geothermal plays of Ingamok and the original paper. And based on that, we identified basically made a mapping of the geothermal play types in Europe. And as you can see on the map, we differentiated among the main play types. And what is even more important, that these play types really follow the geological, let's say, boundaries, so not the state boundaries. So this is really a pan-European map. As you can see, many of the plays are really transboundary. So there was a huge amount of harmonization work among countries along the, let's say, the political borders. And for each geothermal play, we have more than 400 individual plays we identified, and for each play, we prepared a let's say, information sheet, which is describing the main play type, its geology, its main characteristics, the main use type, and the most important literature. And each of these sheet can be also downloaded from this EGEC portal if you click on this respective play type. So this is where we are at the moment with deep geothermal, and of course we are working on the next levels for the more detailed characterization. But what I would also like to show you, what is very often asked, that everybody is so much focusing on deep geothermal that sometimes shallow geothermal and underground thermal energy storage, which we know have extreme importance in Europe, is somehow neglected. So we try to deal with this in this portal. And we are also preparing a similar pan-European atlas for shallow geothermal resources and underground thermal energy storage. This work has just started, so this followed the deep geothermal part, so I cannot show you such detailed results. But basically the concept of this shallow geothermal atlas package, let's say so, will be very similar to the deep one, so this pyramid concept. So we have at level 1, we prepare very high coverage, so entire Europe, so a pan-European scale, but with a, let's say, showing a low level of knowledge, so a very generalized knowledge, which will be mostly based on the interpretation of the European hydrogeological map, which is a 1 to 1.5 million scale, and other different large-scale EU heating, cooling, demand maps. And at that level, we are planning to produce 2 different maps. For shallow geothermal, it will be a so-called favorability map for ground source heat pumps, or both for open and closed loop systems, which is very much based on the suitable hydrogeological conditions. And for the low temperature underground thermal energy storage, so for ATES and beta system, is also a suitability map, whether the hydrogeological and climate energy demand conditions are suitable. So this will be the level 1, let's say, pan-European map. And then once these maps are ready, we are now working on this, we will move to let's say, medium level of accuracy for national to regional scale, and then hopefully at some pilot sites to regional to city scales. At this level 1, what we are, or basically not me, but my colleagues are working, so this favorability map for ground source heat pumps and for low temperature thermal energy storage systems. The methodology which the experts are using is this so-called multi-criteria decision analysis in a GIS environment. So they are, from the data which they have collected, they are selecting different parameters like aquifer productivity, different types of chemical composition, and also for the thermal energy storage, the energy demand, and they are making this weighed comparative analysis of these basic parameters. And how it will look like, hopefully very soon in the future. So we expect to have these 2 base maps coming out in, hopefully second half of this year. Will look like this. So this is just prototypes for both maps. So again, a general overall pan-European map showing the like a traffic light map showing the favorability for ground source heat pumps and for UTES systems. So why all this information and knowledge is important for Europe? Well, we all know, and we are all very excited to see the final version of the Geothermal Action Plan coming out now in June, as I know. And the Geothermal Action Plan, of course, it's a very complex document focusing on a lot of different areas, but data availability is definitely one of the key areas. And what we would like to position the European Geological Data Infrastructure Platform is as a key part for this Geothermal Action Plan, which will be a major feeder for the data availability for all, let's say, geothermal-related actions in Europe, whether it is a question of mapping global scale resources or information for decision makers. So, for example, which are the favorable areas for ground source heat pumps, or the identification of renewable go-to areas for geothermal to underpin risk mitigation schemes. So I don't want to, I guess these are all very well known to all of you, that data, and especially reliable data and open source, openly accessible data, are really the key aspects of many parts where geothermal can really rocket fast and develop very fast in the future. So thank you very much for your attention.
Thank you, Annamaria, for your very interesting presentation. And I think we have, last but not least, Stefan Carpentier from TNO. He will present how AI can be applied more specifically to geothermal resource mapping. So Stefan, the floor is yours.
Thank you very much, Luca. Yeah. Let's see. Do you see a full screen presentation?
No, not
You
yet.
don't. And how about now? Also
Still
not.
looks like you're sharing nothing.
Yeah, so it's still not good. It's not a title screen.
No.
And
There is no sharing at all.
there is no sharing at all. Okay. Let me try again. How about now? Is it better?
Yes, now it's good.
Very good. Yeah.
Thank you.
Thanks. Yeah, indeed, I have the privilege to end this session, which was really, really amazing in terms of the geothermal exploration and mapping activity is actually also beyond my expectations. Really exciting to see, and I'm gonna zoom in a bit on more regional, even local models, because when we identified geothermal potential, at some point we need to put a drill bit in the ground and make pipelines and all these things, and we should really de-risk the subsurface in a very detailed method to get investors and insurance companies on board. So for that reason, the Geological Survey in the Netherlands, GDN, is actually mapping also for many years already what the GSEU presentation was just showing. We do on a national scale, just like many other surveys. But we see that generating these models of basically lithology, but also heat flow and density and gravity and whatnot, and even hydrological models, it takes a lot of effort and resources to produce. And at this moment, every 5 or 10 years, we revise the models and bring out new models. But this is not the pace at which exploration is done. Exploration is done much faster and much more frequent and more financially driven. So for that reason, when people do exploration, geothermal exploration in the Netherlands, they usually do a detailed geological study, a local geological study, to actually get a very detailed image of the subsurface, the depths, permeabilities, because they often complain that the geological survey model that we have is not detailed enough. So we would like to increase the frequency of modeling and also basically improve, accelerate, and objectify the mapping that we do. So for that reason, we are moving towards implicit modeling, relative geologic time models. So basically what you see here to the right is sort of a conceptual idea of what we are moving towards. It's basically not stepping away from classical geological modeling by experienced interpreters, but basically using their knowledge to more on the fly, on demand, and faster generate models like this that are based on input data, expert knowledge, and then a really fast generation of these models. Then we're talking about seconds, minutes, hours in that order, not like 5 or 10 years. And then we can, as soon as we have new information, new measurements, new knowledge, new expertise, we can just update the input parameters and on the fly generate new models of implicit models with relative geologic time. Relative geologic time is essentially something that you may have encountered in other platforms and software like Petrel or PaleoScan or other major packages, where you basically model the geology as being a potential field of equipotential lines which correspond to depositional surfaces. And if you can model these depositional surfaces with input using all kinds of physics and algorithms behind it on the fly, it's a very powerful method. But it does need a really good input data. So it does need to some degree 2D, 3D seismic dips, guiding seismic horizons, units, facies, faults, well tops, markers, and any other geologic context. And these data are hard to get by sometimes, especially in data poor regions. So we have developed an AI-based workflow, which is supposed to predict basically these input data, so horizon units, well logs, at places where we don't have them. And we basically do the philosophy of training neural networks in data-rich areas, where we have a lot of 2D, 3D, a lot of well coverage, and then learning there how the physics, how the relations between all these properties are, and then predict in data-poor regions, where we have a couple of leads, a couple of base data, and based on these base data, we can predict the rest. And that's a bit the philosophy behind this workflow, which is supposed to deliver the input data for the implicit modeling. So, and we have divided it for now in 4 steps, where the first step is really conditioning existing data to improve sparse data that you may have. Then the second step is to produce AI-assisted interpretations. So actually that you can rapidly on massive scale produce horizons and basis maps without the requirement of manual picking, which can take years. The third step is to produce really reservoir properties based on logs and seismic. And the fourth step is really bringing it into the implicit models. And we're working in several European projects on this. So I start with the data conditioning part. So we're really focusing, zooming in on a little piece of subsurface land, which is, let's say, underneath the city, next to the city, meant for a prospected geothermal plant that we have identified based on the knowledge of the previous speakers. And I'm going to deep dive into AI. I'm not going to explain the algorithms in detail, but we're using several algorithms that are really meant to condition, to improve existing seismic data and log data, which are old, they are vintage, they have gaps, they have noise, they have all kinds of problems. And they are, as such, not suitable. Sometimes not even suitable for human interpretation, let alone for AI interpretation. So we need to improve these data to get rid of noise and to fill in the blanks. And we can fill in the blanks nowadays using expert geologic knowledge that has been entered into neural networks. And I'll spare you the details, but there are some really nice publications on this, where you can basically, based on the knowledge of having seen thousands and millions even of seismic data, geological models, you can predict what are the plausible continuations of reflections where you are missing them. So you can basically fill in the blanks, and you can remove anything that you know is noise. So we move to the next. So for example, we have a typical seismic data set like this. This is not uncommon in the Netherlands that you have vintage data, which was recorded in the 70s, in the 80s, sometimes 60s, but also more modern. And you often have gaps, which are usually worse in the shallow domain where you want to do U tests or A tests or low temperature storage or production. Well, if your system falls into such a gap, that is a shitty deal. But using AI, which is now trained on millions of models, we can basically fill in these blanks really profoundly even. And it looks like magic. And if you look in the very top, there is a degree of geofantasy there. But we can put a confidence on how well the data was predicted in the gaps based on how shallow it is and how much surrounding data is there. But in general, we have found by blind tests and by looking at well locations that actually this is a very plausible conditioning of data. And also a lot of these shallow noisy events were also suppressed hugely. Now this data is something that AI can work with, because if we now let some kind of AI assisted method interpret these sections, it will know what to do. Instead of this, it will not know what to do. So if we go to this next step, which is AI assisted interpretation, this is essentially, it's not replacing seismic interpreters, it's just using their knowledge, their logic, their way of interpreting things, and just extending that to 3D volumes. So without going into detail in this method, this is a class of neural networks that's called semi-supervised, meaning that a neural network can start with only a limited amount of examples of interpretation that a human interpreter gives to the model. So you need only 1% of interpreted, annotated data in a seismic line or a cube. So that's considered sort of a data poor scenario where we have hardly any data or interpretation. And the model will make a prediction and can judge its own prediction if it is a good prediction or not. If it's a good prediction, it will take this prediction and train on that. So it trains on its own good examples. So it's sort of reinforcement learning. And an example of how successful that can be is that you have here on the left side, you have true ground truth cross lines in a seismic volume, which were actually not seen by the training data. So adjacent other sections were used, but not these. These are blind lines. And this is what the AI has reconstructed on this blind test. So it hasn't seen it, but based on the seismic, it made this. And this is the error that you see. So the error between the prediction and what is really there by a human being is getting really low. So it's getting workable. And if you do this on a 3D seismic cube, which I do not consider data poor, I mean, this is a data-rich scenario where we know the ground truth, but we can do this prediction on 2D lines, sparse lines in a data poor area. But this is just to check, and we can see that these Kleiner forms are really well interpreted based on only 11 inlines in this seismic cube. So you do your interpretation speeds up by orders of magnitude, and you can predict, train and predict on massive amounts of data that have never been interpreted before. So this is really speeding up the input data. Same goes for faults. I mean, there's a lot of algorithms nowadays, also in mainstream packages, also like Petrel, Paleoscan, that do automatic fault picking. So essentially, it's also the method we use is self-supervised. It's a method that can assess its own predictions and then train on them, and requires only 1% of examples. And if you do that, then this is typically what we can achieve. Also a data-rich scenario, I admit. But if you have a cube and we know the ground truth, we know what people have interpreted before, and the AI can reproduce this very, very well. And it works on 2D lines as well. So we can actually predict on old sparse 2D lines as well, and then connect up the faults. So what we learned in this scenario is now going towards data poorer regions. And the same goes now in step 3 for predicting blocks that we didn't have, or they are not interpreted yet. So we can actually do two things. We can either interpret logs that we already have. And so let's say this is from an international benchmark log set in USA, where we have gamma ray, induced resistivity measurement, porosity, and some other things. photoelectric. And the ground truth of the facies that was interpreted by expert petrophysicists is this. This is a facies. And the CAN, which is actually the model name, has predicted based on these logs, basically these formations. And as you can see, it is a lot of correspondence. Actually, the F1 score is 0.62, which on real field data is considered a fairly high score. It is a bit less than a petrophysicist would do, but it's still pretty good. And the major units are really well predicted, but some underrepresented sort of exotic units are still not well predicted, but we're getting there. So it's also starting to get workable, and it goes really in milliseconds, this prediction. So we can interpret logs, but we can also create logs where they were not yet present. So for example, this situation where we have a blind well, which was not seen by the neural network that was trained, it was in this case an XGBoost network on another benchmark log. And we have done this exercise on Dutch data. It works just as well. So in blue is the blind porosity log. So porosity, of course, very determining for geothermal exploration. This is actually a very deep situation. And the orange is what was predicted by the neural network based on auxiliary logs. So based on the gamma ray, based on the caliper and these things. So it's getting awfully close to the truth, to the point that we can allow it to do these predictions or generate logs that we have confidence that these are correct logs. So we can actually also predict certain logs from certain log runs that we omitted certain expensive logs. We can actually have AI predict them and save a lot of cost and still have geothermal parameters. We can do the same trick on seismic. So here we had only in one well isolated logs, but we can just as well have a seismic section constitute a whole number of sort of pseudo logs, stacked next to each other, and we can do the same trick. So we can have a seismic line and multiple wells that are intersecting. We teach the seismic and the co-located well how they are related, and in this case, we trained a seismic section on sand, shale, and grain size things. So actually, we can already predict from seismic now sand and clay and grain size variation, and we get very realistic portioning upward sequences. And this is actually in the domain of ATES and UTES. So we actually use this prediction to plan and build a ATES system on the Utrecht University campus, where TNO is located and the Geological Survey. So we are doing this stuff in our backyard, and it really works. And we actually have confidence that we take financial decisions based on this. And to finish up, all these input data that are now, they're trained, predicted, validated on blind wells, cross-checked, and slowly we're getting sort of convinced that it's working. These input data will then go into these examples where Diederik van Wees is actually very active in this development, to put these horizons and markers and well markers all into this implicit modeling, and then we get models such as these, which combine faults, seismic dips, and all other things. And this can also work in 2D data for situations that we get on-the-fly models that include all the geological elements. So it's really a powerful combination. There are definitely some flaws where we are still not able to model properly very complex geology with incredible faults and things like that. But we are really on the way, and this is going to really transform geologic modeling and geothermal modeling as we know it. So thank you very much.
Thank you, Stefan, for a very interesting approach to the use of AI in geothermal. I think it's we're all looking at this to make geothermal more scalable for sure. And I think Philippe, maybe I can turn it back to you for your final considerations.
Yes, it was promised at 2 o'clock that there will be a lot of information to share to you. It's recorded. Presentation will be shared when possible. Indeed, it will deserve our conversation. The first time we do a webinar about this topic, but we see that there's a lot of unnecessary reaction from the participants, and the interest to join this webinar was really great. So really good to have initiated a first discussion on such a topic, which deserve probably more attention, as I say, not only with webinars, but probably with a physical event to have a discussion. On physical event, I can also announce next event from EGEC. The next one is probably not yet announced. It's only for EGEC members. Next Thursday, we will debrief to you the Accelerate EU initiative from the Commission with really great provisions on geothermal energy. As mentioned, it may also contain the creation of a European geological database. If not, all that will be in a physical event, 4th of June, the EGEC Policy Summit, where we'll discuss indeed the Geothermal Action Plan, but also Accelerate Europe and other activities. So I invite you, all of you, on 4th of June. And if you're arriving the day before, on 3rd of June, we have also the traditional EGEC summer cocktail. If you're dealing with geothermal district heating, we invite you to Dublin, 3rd and 4th of September, for the traditional GeoDH days. And last but not least, we have a special event for Central and Eastern Europe this year, and we'll be on 29th of October in Bucharest for an event which will not cover Romania, but will cover Central and Eastern Europe. With that, I think it's time to conclude the webinar. Presentation will be shared, recording will be available, and I wish you a good end of the week and a good weekend. See you, bye-bye.